Okay, so we're going to discuss the second part of the frequency response. Last time we talked about the low frequency response. So if it is a capacitively coupled, there's a role of at the low frequency. So today we're going to examine what limits the transistor performance on the high frequency end. And it's mostly the transistor itself, okay? So for high frequency response, okay, and so we kind of go through, hopefully you all have watched the video for Tuesday's lecture. We draw the physical cross sections and determine that the transistors has intrinsic capacitance. These are parasitic capacitance, but it comes with the transistor operation mechanism. So it's impossible to get rid of them. The largest capacitance is between gate and source. So CGS is the largest component. And then there's a much smaller component due to the overlap of the gate electrode and the drain. So there's a CGD here, okay, CGD. And then there are capacitances between the source and body, okay? So there's a capacitance going to the terminal body or substrate, okay? This is called CSB, and likewise, the drain is also connected to body. This is called CDB, all right? This is body. For our analysis in 105, we're trying to simplify and get you to the most dominant results without being bogged down by a lot of detailed algebras. So for these classes, we're going to neglect these two, okay? So CDB and CSB, we're going to neglect in 105. Doesn't mean they are not important. They could become important, but generally the effect is smaller than CGS and CGD. So we're going to focus on these two capacitors here. Okay, and one way to characterize how fast the transistor is, we often use a parameter called FT, okay? FT of a transistor, okay? What is FT? FT is defined as unity gain frequency when the current gain become unity. So the frequency at which current gain is defined as a current gain. The origin of that is that we started from bipolar junction transistor. It's usually a current gain device. So we just carry the definition of this frequency forward for a new type of transistor, MOS. So this current gain become one. So it become a unity gain. So what does it mean? It means if I take, so if I draw an AC equivalent circuit, okay, AC circuit, not a hybrid pi model, just a circuit. If I have a transistor, okay, kind of the simplest case, I have a transistor, I apply a small signal current source, okay, so this is I that I applied, and I evaluate the load with a short circuit. Okay, so I actually short circuit the load, and I measure what is the I/O here. So I should add a condition at which the current gain is equal to 1 for short circuit load. Okay. Why short circuit load? We want to know the intrinsic response of the transistor. We don't want to know the interference due to the external circuit element that we attach to the transistor. So this is the fastest the transistor will go. In a circuit, you usually get a slower bandwidth, lower bandwidth than this FT. So FT is an indication of how fast you can run the circuits. In digital circuit, this is more for analog circuit, but in digital circuit, typical clock rate runs at about 20% of FT. So if you want to design a faster microprocessor that runs at, say, 10 gigahertz clock rate, well, your FT has to be at least 50 gigahertz. The modern transistor, FT is on the order of 100 gigahertz up to about 300 gigahertz. So that's pretty fast. Yes. Frequency of the transistor itself due to these two capacitances. Okay, so now let's look at what are their relationship. What's the relationship for these two transistors? So we draw the complete hybrid pi model. Okay, so the complete hybrid pi model that includes the capacitance looks like this. Initially, let's draw just the small signal model. We have here, this will be VGS, okay? And we have the dependent current source. This is GM, VGS, okay? And we have low resistance, R0, all right? And the hybrid pi model, complete hybrid pi model, includes now CGS, okay? And CGD goes here, right? And this is source. This is source. Source is here. And this is drain. This is a gate. So normally we used to have open circuits between gate and drain or between gate and source. Now it's no longer open circuit. It's coupled by capacitance. Otherwise you will look very odd to feed a current source into the gate. It just sees open circuit. For AC, well, there are capacitance. And capacitance, you can pass AC current through capacitance. So by attaching the circuit element, we will attach a current, small signal current source here. Okay, this is II. And then we will short circuit drain. So we connect it by a short circuit here. And the source is grounded, okay? So the blue color are the simplified hybrid pi model for kind of low frequency response. Together with the red color capacitors, that's the complete hybrid pi model that we can use to evaluate the high frequency response. And the green part are just the external circuit element. So how do we analyze this? This circuit is quite a bit simplified because we short circuit the output. So let's do AC analysis. Let's use the symbol S equal to J omega. It's a shorthand. I think by now you are comfortable using S to represent the circuit element. So the capacitance, CGD, their impedance, okay, their impedance, for example, will be equal to 1 over SCGD, okay? Or in the O formula, it's 1 over J omega CGD. So that's the same, right? And likewise, 1 over CGS impedance is equal to 1 over SCGS, all right? So the rest is the same. We just treat this capacitor just like a circuit element using impedance rather than the capacitance value. So in other words, we treat them kind of like a resistor, except its resistance is a complex value. All right. So we do we do basically KCL. So if we do KCL at drain, KCL at not drain, at gate, at G, we'll see II is simply equal to, there are two current paths. And this is actually ground. So the ground extend all the way there. So I can just simply put the ground here, all right? This is because of our short circuit load, okay? So this is actually equal to two paths. It's VGS divided by the impedance of CGS. So it's 1 over SCGS plus VGS divided by 1 over SCGD, okay? And you can actually simplify the two terms. It's a VGS times SCGS plus SCGD, all right? So that's a KCL at the drain. And then we can, what are we trying to find out is the current flowing here. So IO is the current flowing through the short circuit load, okay? So let's do KCL at drain, right? And you'll find IO, output current. There are a few passes. Actually, you can see this R0 has no effect. Why? Because top side is grounded, bottom side is also grounded. So by short circuiting the load, there's no effect for RO. So that kind of simplify our analysis. So the KCL here is becoming simpler. This is equal to the current going out of the node. So that's this term, GM VGS, okay? And then there's a current flowing to the other side, okay? So this is flowing out. So this is plus 0 minus VGS divided by 1 over SCGS. So that would be the current. Okay, so this is equal to GM VGS minus SCGD times VGS. So both are functions of VGS. So we just substitute VGS from here into this equation. So IO is equal to, CGS is basically II over SCGS plus SCGD times this term, 1 minus CGS, so GM, sorry. So this will be GM minus SCGD here, all right? So our current gain, AI, current gain is IO over II. So this simply equal to GM minus SCGD, okay? And this is SCGS plus CGD, okay? Any questions here? Yep. KCO at the drain. So this is drain. This is a drain terminal here. Let me switch to a yellow paint. So this is the drain here. And I mentioned we ignore R0. So basically IO comes in here, right? IO goes all the way here. So this is IO. There are two paths out. This one path, okay? And this is another path. We did not ignore CGD. So there are two terms. This is the first term is here. This is first term. And second term is a current going out this way. So this is the second term. CGD. The current path flow through the second is from here. So it's the terminal voltage between CGD. So the voltage here is VGS, right? And the voltage here is 0. So I have 0 minus VGS, 0 minus VGS here. CGD, sorry, you called me a mistake, sorry. Yes, you're right. This is a CGD and CGD, actually. The rest of the equation is correct. Okay, all right, so, and now we have this current gain, and GM is generally much bigger for the frequency of interest. SCGD. CGD is usually a small number, okay? CGD is usually very small, smallest of all capacitances. So usually very small. So we kind of, for practical purpose, we can actually ignore this term, all right? And so we just have GM over CGD, okay? So if we look at the frequency response of this short circuit transistor, okay, if we plot the Bode plot, but the vertical axis is log AI, right? You can put 20 here, but doesn't matter. And the horizontal frequency will be omega. And this is basically 1 over omega dependence. So it's basically a straight line going down, something like this, okay. It crossing this point is what we define as FT, omega t. Omega t is equal to 2 pi times FT. That's the transit frequency. So FT, actually, I forgot to explain. So FT is called transit frequency. But FT is so commonly used by the community. People just loosely say FT of the transistor. So what is a unity frequency? Well, we just set AI equal to 1. And this means GM over J omega CGS plus CGD. This absolute value is equal to 1. So it's kind of straightforward to get omega t is GM over CGS plus CGD. Okay. If you want to further simplify, you can just say this is GM over CGS, because CGD is usually much smaller than CGS. So this is a fundamental frequency response of a transistor. It's very difficult. It's, next to impossible to design a circuit that has a functional gain beyond the FT. Usually that's not possible. So this is the upper limit. If you design into, say, a technology node, if you become a circuit designer, you'll say, you pick a TSMC 10 nanometer node, and FT is 300 gigahertz, okay? And you kind of know what type of circuit you can design into this. If people say they're going to design a terahertz signal, well, they need some magic to make it work using that technology node. Okay, so that's FT. Depends. The question is it better at the higher frequency? Oh yes, terahertz frequency is primarily used for sensing. You go through airport, I think there's a body scan. They claim that's called terahertz scan image. In reality, it's just a millimeter wave. It's slightly below terahertz. but terahertz sounds fancier. But if you do have an efficient terahertz source, it can be imaging concealed weapons, people carrying weapons going through. You cannot see with visible light, but terahertz, you see exactly where the weapons are. That's why it's of interest. As a wireless communication, it's very difficult to generate terahertz and detect terahertz. So it's not going to displace the wireless communication anytime soon. It's more used for the niche application. You can only see with terahertz. Okay, all right. So let's now, we are equipped with this tool. So let's look at the frequency response. So high frequency response, okay? High frequency response of CS amplifier, common source amplifier. Okay, so just as a reminder, what is a common source amplifier? Well, it's there's a RD here, and there is a common source, and we'll be applying signal here. Okay, so here is VI, and this is R. Let's call this RS, source resistance, and we'll be driving RL. Okay. And if we now start to attach the capacitors, okay, so there's a CGS here, all right, CGS, that's kind of okay, it's connecting to ground. It's actually very easy to analyze that. But we have this CGD term, which connect from input to output. It's a kind of a feed-through capacitor. Your signal actually doesn't always go through the transistor and then go to your load. Yeah, you can see this CGD as a feed-forward path. It just feeds the signal directly to the load, okay? So that's an interesting aspect of capacitor, yeah. Yes, yes, that's true. There will be two components, but in when we do the small signal hybrid pi model, we will include everything. So you'll get a response, but yeah, there are a part that's coming from either term. So, okay, how do we analyze this? Okay, now we are equipped with the hybrid pi model. Okay, so let's draw the hybrid pi model. And then there is R0, GM, VGS. There is R0, okay. And I can combine RD and RL1 since the AC circuit, they are both connected to ground, okay. So I have RL prime, which is equal to RL in parallel with RD, right? And this is my output voltage. And here I have RS and I have VI, right? And then I attach the capacitance. So I have CGS here, and I have CGD here. Okay, and the source is grounded, and VGS is still defined as the voltage drop between gate and source, right? Well, this looks still very straightforward, very simple. And however, I would encourage you to do this. I was tempted to give you this as a homework problem for you to solve this. This will be kind of on the more complicated side by hand analysis. This CGD really caused a lot of trouble. So, you know, CGS used to be very well defined. It's just VI, but now it's a VI. Well, you know, part of the current go this way, part of the current go down. It's becoming very complicated to solve. And you get two-pole response. which is in the lecture notes. I'm going to skip it here. I'll just say direct solving, okay? Solving using KCL, KVL. That's still a golden rule. KCL, KVL, you can solve anything. As long as you are patient, you can solve anything. So this still works, okay? But tedious, okay? And tedious, once it becomes tedious, we lose sight of our intuition. And when we're doing hand analysis, the intuition is very important, or sort of to guide you towards designing the circuit that you that will work for your application. Intuition is very important. So instead of going through this exact analysis, there's some ingenious pioneers in circuit theory that found there is a simplified method, okay? And simplified method is an approximation. It's not exact, but it's usually very good approximation. So this is called Miller effect. Okay, so Miller effect is not just applicable to common source amplifier, but it applies to any amplifier. So this is an amplifier with a voltage gain of AV, all right? And input, output, okay? So we have VI, we have VO here, but there's some elements that's connecting from VO to VI, okay? Let's just draw a box for this element. It could be a resistor, could be a capacitor. I'm just going to call it impedance, Z, okay, ZF. It's feeding forward, or you can say it's a feedback. They kind of affect each other. But there are additional components that's connecting it. So now if we ask the question, what is the effective impedance that you look in here? Z in, okay, effective impedance. Assuming, you know, the impedance of the voltage amplifier is infinite. So basically we're just looking at what are the effect of these elements hanging between input and output. What are the impact in terms of the impedance looking in there? Okay, so this is actually very straightforward. Z in, okay, is basically equal to the voltage difference. So it's equal to V in divided by I in, all right? And V in is the input. Sorry, I use VI, so let me just do VI over II, and where is II? II is here, II, all right? So this input impedance includes this ZF effect, okay? So VI is still VI, and II, if I assume all the current, actually, if I assume all the current, II go through here. There's no current going in, so no current going in here. Kind of ideal amplifier, the impedance is very large, all right? Then II can be quickly estimated by VI minus VO and divided by ZF, okay? And VO is equal to voltage gain AV times VI, right? So Z in is equal to VI minus AV VI times ZF. VIO cancels out, so Z in is equal to basically 1 over 1 minus AV times ZF. Okay, so it's ZF divided by 1 over AV. Second equation should be ZF, yes. ZF, yes. Okay. So now let's turn our attention to the capacitance. So this is an area where it has most impact. So now let's consider ZF is equal to 1 over J omega. It will be CGD, but let's just say it's a capacitance load. So 1 over J omega C, all right? And so Z in will be equal to 1 J, sorry, it'll be, yes, we can have J. J omega C times 1 minus AV. Okay, and if we say this term is equal to a new capacitor, so this is equal to 1 over J omega. This capacitance we call Miller capacitance. Okay, so to note this is a Miller effect. Then you will say the Miller capacitance is equal to the original capacitance times 1 minus AV. Okay, so you have a Miller capacitance connecting to ground. So what are the benefits of this? The benefits of this is I have eliminated the connection between input and output, which makes our analysis tedious. Okay, now this Miller capacitance is directly connected to ground. So this C Miller here, and here's VI, all right? So these become very easy to analyze. All the complexity have disappeared. So let me redraw the amplifier, CS amplifier. So CS amp with Miller capacitance, replacing, okay, replacing CGD. Okay, so let's see how it looks like. So we have an RS, same, okay. We have VI, the same. And here we have dependent current source, GM, VGS. And we have R0. And we have RL prime. Here is VO, okay. And we have CGS, okay, CGS, right? And now we have this new Miller capacitance. This new Miller capacitance is connected to ground also, okay? So this is a C Miller here, right? So now you noted that we have regained our simple circuits. The input is one clump, output one clump. There's no connection between input and output. That makes our analysis simple again, okay? And you further noted that these two capacitance are in series, in parallel. Capacitance in parallel, you just add their capacitance. So this you can replace with one single capacitance with a CGS plus, I substitute the Miller capacitance, 1 minus AV, okay, times CGD. Okay, so that's just one capacitance. And if there's no low capacitance involved, you can see this is a single pole response, right? So frequency response is trivial. Basically, you can write out the whole thing. Your VO is equal to GM minus sign. Let's keep the minus sign here. Minus sign GM VGS times RO in parallel with RL prime. Let's call this RO in parallel with RL prime. Let's call that RL double prime, okay? And VGS, what is VGS? VGS is simply a voltage divider. It's a VI times RS plus 1 over J omega C, where C is equal to the whole thing. Let's call this a C input, C in. Let's call this C in equal to both terms. And the voltage is dropped across the capacitor. So 1 over J omega C in. And then we have RL double prime. So let me just say RL double prime. So you can separate that into two terms. Your AV is equal to basically the low frequency term is minus GM RL double prime. This is a DC value that we have obtained earlier. But then there is a frequency dependent term now. It's 1 plus J omega RS C in and 1. Okay, this is the frequency response. So this term gives you the high frequency response. And so without, it's almost trivial after we substituted by Miller capacitance. It's almost trivial now. So this is a low pass filter, right? So you know the frequency response is something like this. If we draw the Bode plot, okay, this will be my high cutoff frequency now, okay, high cutoff frequency. So this will be log AV 20, and this is my omega here, single pole response, except compared with filters, the baseline here, it gives you gain. So this gives you low frequency gain. Sort of the gain we obtained earlier without considering the capacitor, okay. And omega h is basically equal to 1 over RS C in, and let's substitute C in. RS times CGS times, okay, we have 1 minus AV here. What do we use the AV? This AV, well, we don't use the frequency dependent term here. Otherwise, we just go recursive. This is a never ending story. So here we just use the small signal DC gain, basically, just use the DC gain. So in other words, DC gain, AV is simply this DC term is minus GM RL double prime, okay? So we'll put that in here. So this will be 1 minus, so there are two minuses. So it becomes plus GM RL double prime, okay, times CGD, right? So you see the response, in addition to the gate capacitance, the CGS that we normally see, because of the Miller effect, the capacitance has increased a lot, okay? So remember that GMRL, this is a large number. This is a gain, right? So it's a large number. And you have multiply CGD, which normally is small. Now you have boosted up by this DC gain. So now you have significant RC loading now. Okay, question? Omega h depends on the value here, this expression. High frequency means, what does high frequency mean? So amplifier, a typical amplifier, frequency response This is at the beginning of the lecture last time. If we look at the Bode plot, usually it's something like this, the band, kind of a bandpass behavior. So we call this part high frequency response. The actual frequency could be very low if you use a transistor with really large CGS. Right? Yeah, just the right hand side of the Bode plot. And so this is omega h, and here is omega L, low frequency response. It doesn't literally mean the frequency is very low. Yeah, okay. Okay, so this is a powerful effect. So now you can build that into your intuition. Common source is a nice gain stage, but there's a gain bandwidth product. So you can sort of see there is a gain bandwidth product. So for CS amplifier, there is a gain bandwidth product. So what is gain? This gain bandwidth product, G gain bandwidth product is equal to, what is gain? Gain is, let's take an absolute value. So it's a GM, okay, RL double prime. And what is bandwidth? Bandwidth is omega h. If we assume the second term dominant, then the bandwidth is, let me put an approximate sign here. The bandwidth become RS CGD and times, let's ignore 1. So there is a GM RL okay. So that's the bandwidth, gain bandwidth product. So you see, if you have high gain, if you design this to have a high gain, well, your Miller effect gets larger. So your bandwidth will go down, okay? The product of the two stay constant. The product of the two, you can say, well, these two terms cancel out. The kind of a fundamental figure of merit for this amplifier is 1 over RS times CGD. So if you want fundamentally higher gain, higher bandwidth, well, you have to use a transistor with a lower CGD or carefully design your RS so your RS doesn't load it down too much. Otherwise, if you stick with the same transistor, there's always this gain bandwidth product. You can use higher low resistance to boost up your gain, but be prepared when you do that, your bandwidth response will go down. Okay, so this is, if you recall our discussions before, if you increase your gain, we basically stay in this line, same gain with product, and you will arrive at higher DC gain. Okay, so this line means you are moving with the constant product behavior. Okay, you can go to higher gain, so this is higher gain, but the frequency response is lower. Okay. We encounter this in OPAM, finite bandwidth of OPAM. So that's exactly the same phenomena. And actually, these are very general phenomena that eventually give rise to the OPAM's constant gain bandwidth product. Okay, good so far. So this response, this frequency pole, so we say, well, the frequency pole is this. What happened if you go do the exact KCL, KVL? If you do a full analysis, full KCL, KVL, okay, the expression, I'll just give you the expression. The pole frequency is equal to 1 over, you'll see some similarities. This is RS times CGS plus 1 plus GM, RL double prime, CGD. So far, so good. It's almost as good as the exact expression. It missed out one term, RL double prime times CGD. Okay. So the Miller effect, it's an approximation. It really applies to the input side. So we see that, well, there is some interaction with the output side as well. All right. So it's close. So just remember that Miller effect, Miller capacitance is an approximation. Okay, don't treat it as it's exact. Okay. What about other amplifiers? Is there any question before we move on to the next amplifier configuration? So we talked about three kind of canonical single stage amplifier topology. So CS, we look at the CS now, both AC and DC. So let's look at the common drain, CD, common drain amplifier. So common drain amplifier, let's say the circuit will looks like something like this. The drain is connected to VDD, and VDD is AC ground, okay? And it will be driven by biased by a current source, and this will be output voltage. Input voltage come from here, and we feed it with VI and drive it through RS. Okay. So how do we do this? Well, we do small signal analysis. So we have drain, we have dependent current source. Okay, this is GM VGS. We have R0. Okay, R0, and the drain is grounded. Source is not. Okay, and here is extension of the source node, and we have RS connected to VI. Okay, just remember RS is not grounded. So let's say, if we think of this current source as a current mirror, if you remember current mirror is, there's a reference, and we go through this current mirror to bias. Okay, this is a current mirror. So if we look into the current mirror, there's a finite resistance. It's not open circuit. If you look down here, let's call this ROC, open circuit. But it's not really infinity. It's a finite resistance. So let's keep that. Let's keep that. And ground is really here, ROC. If we look at this simple circuit, this ROC will be simply equal to RO of this bottom transistor here. Okay, but let's keep it general. So let's just call this RO of the current source, ROC, RO of the current source. Okay, and then we load it with capacitor. So we have CGS, we have CGD. Yeah. Okay, looks a little bit complicated, but not really too bad. Where is RO? VO is here. Is there a Miller capacitance in this circuit topology? Is there a Miller effect in this circuit topology? Yes. And which capacitor will see Miller effect? CGS. So now CGS will see the Miller effect. So Miller applies to CGS. Okay. again, we can do full-scale analysis, but we just learned the Miller effect. So let's try to exercise our what we just learned here. Okay, so let's say, well, our C Miller is equal to 1 minus AV times CGS here. What is the voltage gain for common drain amplifier? Unity, okay. It's a slightly less than unity, but almost unity. So AV is almost 1. It's always less than 1, but very close to 1 for common drain amplifier, which means C Miller goes to 0. That's nice, nice gift for this amplifier. And it's not surprising, okay? I can give you kind of a physical intuition of the Miller effect. So the Miller effect is like a seesaw, or like yeah, exactly like a seesaw. A voltage amplifier. So you can think of voltage amplifier as something that's fixed at the fulcrum here, but the output lever is much longer than the input lever. Okay, so when your VI, this is your VI, this is your VO. Okay, so as you try to change VI a little bit, your VO changes a lot. But if you're charging a capacitor, between these two nodes, what is the total voltage? What is the total voltage that you need to charge the capacitor? The total voltage is actually not VI, not VO, but sum of VI and VO. So you are actually charging the capacitor with this big voltage. And therefore, the larger the gain, the larger voltage you need to charge, which means you need more charge to reside on that capacitor. That capacitor becomes effectively larger, okay? What about CD? So if we use the same analogy, this is a seesaw, but this seesaw literally doesn't move, okay? For unity gain, okay? It's like VI is here, VO is here. The whole thing goes up and down together. VI goes up, VO goes up. VI goes down, VO goes down. So if you are trying to charge this capacitor, well, literally, you don't need to charge it. Both sides always have the same voltage. Therefore, the capacitance is as good as it almost is not present. It's not there. So it's a nice effect of this Miller. So once we remove that, the circuit becomes simple. We literally just take out. Okay, we can actually just use the same circuit drawing here. Let's just take out this capacitance, because Miller effect is almost 0 now. So we have a very simple expression here, and we can just do analysis maybe at KCL at source. Okay, so if we do KCL at source, we have current coming in. It's a GM VGS. Okay, current coming in, and current going out is equal to current going out. That's VO. There are two paths in parallel. One is goes through ROC. The other path goes through RO, both connected to ground. So I'll connect them together here. This is RO in parallel with ROC. All right. And I just have to connect VGS to VI. Okay. So VGS is here. VGS is here. And well, it's no longer just separate to drain. It's actually connected to drain, but drain is connected to ground. So VGS is simply a voltage divider. VGS is simply RS plus 1 over SCGD, and the voltage drop is R1 over SCGD. Okay, so if you look at, let me shrink it a little bit. If you look at the circuit here, this is the voltage divider. This is the voltage divider. Okay, it is ground on the other at the drain, so you can simply use the voltage divider expression. Okay, so if you combine the two, it becomes quite simple. So we can simplify this a little bit. This is 1 over 1 plus S RS CGD. So this is again a typical low pass filter, right? And so you say VO is sorry, we need a VI here. VI, cannot drop VI. So VO divided by VI is equal to, did I leave one term out? I left out one term. Here should be more than one term. GM VGS, this term here, VO, GMVO, GM, sorry. Mistake here. VGS. So this is not VGS. So jump too fast. This is VG. This is just V at the gate. S is no longer ground, so we cannot jump that fast. Okay. So VGS is actually equal to VG minus VS. VS is actually the output terminal. So VG minus VO. Okay. So we should substitute this back in here. So GM times VG minus VO is equal to VO and RO in parallel with ROC. So we need to move VO to the other side. So VO times GM plus 1 over RO over ROC should be equal to GM times VG. And we substitute VG in. This is equal to GM times this low pass response, 1 plus SRSCGD times VI. So now we have our full voltage gain, AV equal to VO over VI. This is equal to GM divided by GM plus 1 over RO parallel ROC, okay? And times the low pass response, 1 plus J omega RS CGD. Any questions here? So we get two things. We get our low frequency gain, okay? You say, well, didn't we already use it? We say it's 1. Now we obtain the expression that's not 1. But noted that the GM is much, much larger than RO in parallel with ROC. So indeed, this AV at the low frequency is approximately 1. Okay, this is approximately 1. But we get the exact expression now. We also know how much smaller it is away from 1. It's pretty close. If you plug in typical number, this will be like 0.99. Okay, and then you get these single pole low pass filter. Okay, so if we turn to our Bode plot is like this, omega, and if we plot 20 log AV, okay, and if we call this 0 dB at the this intersection here, then the Bode plot will be something like this. It's slightly less than 0 dB, because slightly less than 1, and then when it encounter this frequency, so this is our omega h here now, omega h. And our omega h is 1 over RC. What is RC? It's RS times CGD. Okay. So that's the Bode plot of the high frequency response of common drain. So I have a question here for you. If we just look at the typical amplifier, common source, common drain, which one do you expect to have higher frequency performance? Meaning, which one do you expect to have higher cutoff frequency? High cutoff frequency. The 3 dB frequency. Which amplifier will have higher cutoff frequency? So if we compare this 1 over, so you compare with versus the common source, which is, if you go back here, the Miller capacitance, if we just keep the leading term, which is RS, leading term, this is 1 over RS times GM RL double prime times CGS. So which one is larger? Which amplifier has higher frequency response? Anybody? Common drain? Yes. So say if we say both of them have RS, CGD is already then less than CGS. But common source is further loaded by this gigantic gain number there, GM RL double prime. So CS is a lot slower than CGD, than CD. But you can say, well, you don't have gain. So you have an amplifier without gain, but it's wideband. That will come in handy when we deal with multi-stage amplifiers. Yes. If we go back here, go back to, oh, CGD, sorry, CGD, CS plus this. So, yes, CGD, yeah. There's additional term CS. We are assuming this term is larger than CGS, yes. Yeah, so I'm assuming this is a dominant term, and depends how high your gain is. If you have a moderate gain, CGS is still much larger. Yeah, right. CGS is at least 10 times larger than CGD. So if your gain is higher than 10, then the second term dominant. Okay. For a few minutes here, I'm going to introduce the concept, and maybe we'll reinforce it next time. How do we do quick analysis? So if you watch the video of the last lecture, there's a short circuit time constant method, which we use to estimate the frequency of on the low side, on the left side. What about high frequency, high cutoff frequency? So for omega L, for a quick estimate of omega L, okay, we can apply a different method called open circuit time constant method, or OCTC. So previously it's SCTC, now it's OCTC, okay? So what is this method? This method is, well, you know, same small signal, replacement, you know, voltage source, short circuit, current source, open circuit. These are all kind of standard now. But how we consider capacitance, we also do capacitance one at a time. So we also consider the effect of one capacitor at a time, okay? Don't know how to write one, okay. One capacitor at a time, okay? But here is the difference. We replace all other capacitors with open circuit. Okay, that's the difference. Then we evaluate, then we find the resistance, find Ri seen by the capacitance, Ci. So assuming the capacitance, we're looking at the Ci. And then the omega H, finally, omega H is equal to all the constant, okay? All the RC constant, RICI, you sum over all the number of capacitances, okay? That would be your high cutoff frequency. It's kind of superposition. It's kind of superposition. Let's say, can we look at the effect of this capacitor being charged? How much time does it take to charge this capacitor? RC is the time. And then how much time it takes to charge second capacitor? And how much time it will take to charge third capacitor? And then you add up all the time together. So this is effectively saying we sum up all the RC charging time, tau. So a circuit, in order for a circuit to work, the intuition is you need to charge all the capacitances. It's kind of a sequential event. You have to have all capacitances fully charged. Then your voltage respond to your mid-band response, your low frequency response, right? Intuition to think about it, okay? So now if you compare with short circuit, SCTC, short circuit time constant, okay? We say this is for omega low cutoff frequency with open circuit time constant. This is for estimating omega H, okay? There's a quick intuition to this. For low cutoff frequency, we're looking at basically a bunch of high pass filters, right? So you kind of imagine your circuit is a bunch of these together. So this is C1, R1, the C2, R2, right? And open circuit, to look at high cutoff frequency, you're looking at a bunch of low pass filters, which the capacitance and resistance switch place, okay? So you say, I want to look at the effect one at a time. Where's the VO? You can say, well, VO is here. VO is here, right? This is VI, okay, VI. So, well, you want to look at one resistor at a time. So we'll look at one RC at a time. That's fine. We'll look at one RC at a time. It's the same. But how should we treat the other capacitor? Well, we still need to reach, VO, right? So this means we have to replace this with a short circuit. So these we have to replace. We have to replace C2 with short circuit. So we have to replace C2 and so on by short circuit. Otherwise, you don't get to RO, right? What about for high pass response? We only want to see the effect of charging just C1. We don't want to see effect of other capacitor. We still need to reach V out. What do we do? Well, you take it out. You take it out. So you replace this with an open circuit. Then you are charging only one capacitor at a time. So we should replace C2 and all other capacitance by open circuit, right? So you don't really need to remember which one correspond to which, as long as you remember which RC is a high pass filter, which RC is a low pass filter. And then it'll become clear. You should use open circuit or you should use a short circuit. Okay, we'll finish up with the high frequency response before moving to multi-stage amplifiers. If you have questions about your midterms, you can stop by my office hour right after this.